There are moments in space exploration when the data comes back exactly as the equations predicted. Clean, expected, textbook. And then there are the rare moments when an instrument sends something home that doesn't match a single model built to describe it. Voyager 1, the farthest human-made object ever launched, is currently sending back one of those moments. And nearly a decade later, the scientists studying it still don't have a final answer. This isn't a story about aliens. It's stranger than that in a way, because it's real. It's peer-reviewed. It's sitting in the pages of a real astrophysics journal right now, unresolved, while the 49-year-old spacecraft running on less power than your kitchen light bulb keeps sending back more evidence for a mystery nobody has solved. I'm your name, and this is Beyond the Stars. Stick around, because by the end of this, you'll understand why physicists keep using words like baffling to describe a signal that, according to everything we knew before Voyager got there, should not exist. To understand why this matters, you first have to understand how far Voyager 1 actually had to travel to find it. The spacecraft launched on September 5th, 1977, on what was, on paper, a modest assignment. Fly past Jupiter, fly past Saturn, send back photographs. Then power down sometime around 1981, mission complete. A successful but short chapter in the history of space exploration. Nobody planning that mission in 1977 was thinking about the 2020s. Voyager 1 wasn't built to last this long. And yet it kept going. Using the gravity of each planet, it passed like a slingshot, trading a fraction of that planet's own momentum for speed, flinging itself further outward than any human-made object had ever traveled. By the late 1980s, it had already become the most distant object humanity had ever built, and it kept transmitting. In 2012, something happened that turned this from an impressive engineering story into something far bigger. Voyager 1 crossed the heliopause, the outer edge of the vast bubble of charged particles that our sun blows out into space, a bubble that contains every planet, every moon, and everything human civilization has ever built or launched. Crossing that boundary meant Voyager 1 had become the first object in human history to physically leave the solar system and enter true interstellar space, the region between stars, and it kept sending data home. Which means, for the first time in the history of our species, we have had a live instrument sitting inside interstellar space, reporting back on an environment that no telescope, no probe, and no model built from the inside of our solar system had ever directly measured. Before Voyager 1 got there, physicists had spent decades building detailed models describing what that environment should look like. These weren't casual guesses. They were the product of rigorous, peer-reviewed theoretical work, tested against everything astronomers could observe remotely from Earth. And almost all of those models agreed on the same basic picture. Interstellar space should be cold, thin, and relatively calm. A quiet, sparse gas drifting slowly between star systems, without much drama happening inside it. Voyager 1 flew directly into that supposedly quiet region, and what it found didn't match the picture at all. Starting in 2017, the spacecraft's plasma wave instrument, a piece of 1970s hardware never designed to operate for this long, began picking up something unexpected. A persistent, narrowband emission. A kind of continuous low hum embedded in the interstellar plasma that, according to the standard models, simply shouldn't be there in the way it's showing up. This wasn't a one-time spike that could be written off as a sensor glitch. It was a sustained signal, recorded again and again, stretching across a region of space more than 900 million miles wide, roughly 10 times the distance between the Earth and the Sun. When researchers published their analysis in the journal Nature Astronomy, their conclusion was direct. Interstellar space is not the smooth, uniform void the models described. It's turbulent. It has structure at every scale, from distances you could measure in meters up to distances measured in millions of miles. The environment beyond our solar system is more complex, more dynamic, and more active than anything our theoretical models had prepared us for, because until Voyager 1 got there, nobody had ever had an instrument inside it to check. Here's where the mystery actually gets interesting, because scientists studying this emission have narrowed it down to two competing explanations, and as of right now, in 2026, they still can't say which one is correct. The first possibility is that this is thermally excited plasma oscillation, essentially the natural vibration of charged particles reacting to their surroundings. If that's the answer, it's still a meaningful discovery, but it fits comfortably inside physics we already understand. The second possibility is something called quasi-thermal noise, a genuinely different physical mechanism, one that would mean our existing models of interstellar plasma density and behavior need to be substantially rewritten. Two explanations, one dataset, and the only instrument capable of gathering more evidence to settle the question is losing power every single year. Before we get to why that matters for the timeline, it's worth understanding just how close this entire mission came to going silent for good, because the story of how NASA saved it is almost as strange as the plasma signal itself. In 2023, Voyager 1 nearly died. For 5 months, the spacecraft kept transmitting a signal back to Earth, but what it was sending was gibberish, scrambled code that engineers at NASA's Jet Propulsion Laboratory, despite decades of experience reading everything this spacecraft had ever sent, could not decode. The cause turned out to be devastatingly simple. A single memory chip inside Voyager 1's flight data system had physically degraded after nearly 5 decades of constant exposure to cosmic radiation, corrupting the software responsible for formatting the very data the spacecraft was trying to send home. In any normal situation, engineers fix a broken component by traveling to it. That wasn't an option here. The chip was roughly 15 billion miles away, and even a radio signal moving at the fastest speed anything in the universe can travel took 22 hours just to reach the spacecraft, and another 22 hours for any response to come back. Every single diagnostic step required a minimum 44-hour round trip to complete. Engineers would form a theory, write a set of instructions, transmit them, and then simply wait almost 2 full days to find out if they were right, all while knowing that a single incorrect command sent across that distance could end the mission permanently, with no chance of recovery. Working through that process for months, the team eventually discovered the corrupted code couldn't be repaired, but it could be relocated. They split the affected software into smaller sections, rewrote each one to function correctly from a new location in the spacecraft's limited remaining memory, and carefully reconnected the pieces to work as a whole again, all through a communication delay of nearly 2 days per exchange. In mid-2024, Voyager 1 came back online, transmitting clean, readable data once again. And what it immediately resumed sending was more evidence of that same unexplained plasma signal, still there, still unresolved, still waiting on an explanation nobody has confirmed. There's a reason this signal matters beyond scientific curiosity, and it has to do with what the heliosphere, the bubble Voyager 1 had to cross to find this signal in the first place, actually does for life on Earth. That bubble isn't just an empty region of space. It acts as a shield, deflecting a significant portion of the high-energy cosmic radiation constantly streaming in from distant, long-dead stars. Every living thing on this planet exists inside that shield right now. And what Voyager 1 is describing, from the outside of that shield looking in, is an interstellar environment pressing against that shield that is more turbulent, more energetic, and more structurally complex than any model accounted for. Scientists don't yet know exactly what that means for the long-term stability of the heliosphere over geological timescales. But the fact that researchers are now seriously asking the question tells you something about how incomplete our understanding of Earth's cosmic shield actually was before the spacecraft got there. The plasma emission isn't the only surprise Voyager 1 turned up at that boundary either. Existing theory predicted that once the spacecraft crossed the heliopause, the Sun's magnetic field and the galaxy's magnetic field beyond it would behave as 2 cleanly separated systems. Instead, researchers found evidence that the 2 fields interact directly at that boundary in a process called magnetic reconnection, where field lines from different sources rearrange and exchange energy. The solar system, in other words, is not magnetically isolated from the galaxy surrounding it. At the very edge of everything we call home, energy is quietly moving between our neighborhood and the wider cosmos, in a process scientists are still working to fully characterize. Now, here's the part of this story that puts a clock on everything. Voyager 1 runs on 3 radioisotope thermoelectric generators, devices that convert heat from the slow decay of plutonium-238 into usable electricity. At launch, they produced close to 470 watts of power. In 2026, that number sits somewhere around 240 watts, and it drops by roughly 4 watts every year. Earlier this year, NASA made the difficult call to permanently shut down the low-energy charged particle instrument, one of the last instruments still gathering data about the very particles connected to this unexplained emission, simply because there was no longer enough power to keep it running. Of the 10 scientific instruments Voyager 1 launched with in 1977, the majority are now permanently switched off. And every year, the team at JPL faces harder choices about which instrument goes dark next, knowing there's no way to turn one back on once it's gone. There's also a very specific date locked onto the calendar that adds urgency to all of this. On November 18th, 2026, Voyager 1 will cross a distance of exactly 1 light day from Earth, roughly 16 billion miles out. At that distance, a signal traveling at the fastest speed physically possible in this universe will take a full 24 hours just to arrive. Send a command on a Monday morning, and you won't get a confirmation it was received until Wednesday. No human-made object has ever been that far from home, and Voyager 1 will cross that threshold while it's still alive, still transmitting, still sending back pieces of a mystery nobody has solved yet. And that's really the uncomfortable core of this story. There's no mission currently funded that could reach interstellar space and independently verify what Voyager 1 is detecting anytime soon. If a spacecraft purpose-built to study this exact kind of plasma turbulence were designed, funded, and launched starting today, it would take a minimum of 2 to 3 decades just to reach the boundary Voyager 1 crossed back in 2012. Which means whichever of the 2 competing explanations turns out to be correct, The only instrument in existence capable of gathering more evidence about it is the same aging spacecraft, losing 4 watts of power every single year. When Voyager 1 finally goes silent sometime in the early 2030s, this question doesn't get answered. It goes quiet along with the machine that raised it, and it stays that way for a generation, maybe longer. Sit with that for a second, because it's easy to let a fact like that slide past without really registering it. Right now, in 2026, the only live scientific instrument humanity has ever placed in interstellar space is 49 years old. It runs on technology that predates the personal computer. It's powered by less electricity than the light above your stove. And it's sending back a signal that 2 competing groups of serious physicists still can't fully explain. A signal that might mean interstellar space behaves in a way our models never predicted, and might mean the shield protecting every living thing on this planet is less understood than we thought. We didn't need a fabricated anomaly to make this story unsettling. The real one already qualifies. A machine built before most of the people studying its data were even born is currently transmitting evidence of a genuine unsolved mystery in physics, and the clock on how much longer it can keep transmitting is ticking down, 4 watts at a time. Here's what makes this different from a lot of space stories you'll see online. Nobody is claiming NASA detected an object. Nobody is claiming the spacecraft made contact with anything. What's actually happening is arguably more interesting because it's confirmed, published, and still completely unresolved. Real scientists, working with real peer-reviewed data, currently disagree about what the space between stars is actually made of and how it behaves, based on measurements from a machine that was only ever supposed to last 5 years. That's not science fiction. That's just space exploration operating exactly the way it's supposed to, by finding something nobody expected and forcing an entire field to admit it doesn't have all the answers yet. If this kind of story is what you come here for, the real discoveries, the unresolved questions, the mysteries that don't need embellishment to be strange, subscribe and turn on notifications, because as more data comes in from Voyager 1 before its power finally runs out, this question is going to keep evolving. Drop a comment telling me which explanation you think is more likely, thermal oscillation or quasi-thermal noise, and share this with someone who thinks the real universe isn't strange enough on its own. Thanks for watching.